Now, Chapter 2, the second part here, deals with matter. The first question, number 12, says, how can you tell the difference between physical and chemical properties? And then give two examples of each. Physical properties are anything that you can see, you can observe, or you can measure without changing the identity. There's absolutely no chance you're going to change the molecular structure of the substance with physical properties. So you can measure length, you can look at the color, you can measure density. You're not going to change it physically at all. Chemical properties, however, you have the chance you could potentially change a substance chemically when you test it to see if it has certain properties. For instance, checking to see if pajamas are flammable or not. Kids' pajamas, flammability is a big deal. That's a chemical property. They either are flammable or they aren't. Both are chemical properties. And the only way to test that is to potentially change them, potentially light them on fire, ignite them. Something's ability to rust. The only way to tell that is potentially changing it from one substance into rust, iron oxide. So if you're looking at a chemical property, ask yourself, could it potentially change if you test this? Quick definitions: flammability, ability to ignite or catch on fire. Density is a relationship or ratio between the mass and the volume. We'll get into density later in the math section. Ductile means you can draw it into thin wires, like copper is ductile. Malleable, lead is a soft metal, gold's a soft metal. You can hammer it into different shapes without shattering. You try to hammer chalk, and chalk will shatter into a zillion different pieces. Chalk is not malleable, whereas other metals are. Solubility, how well substance dissolves in a liquid. You all know that salt can dissolve in water very well, but the oil, for instance, is not soluble in water. So how well it dissolves in a liquid. It doesn't have to be water. You could be trying to dissolve salt in oil, for instance. See how well that goes. Boiling point. This is a specific temperature at which a substance will start to boil or change from a liquid to a gas. So you should be familiar with all those different definitions. Now you should be able to look at substances and decide, is it a solid, liquid, or gas? Something that has a fixed or definite shape is going to be a solid. Liquid and gas, their shape varies based on the container, which is letter B. Has a variable shape. Liquid and gas, they both depend on what container you put them in. C has a fixed or definite volume. Both solid and liquid. Kids get mixed up with the liquid one. Liquids do have a fixed and definite volume. It does not change. If I take 10 milliliters and I pour it from one cup to the next, it's still 10 milliliters. Gases will change. If I put it in a bigger container, it takes up more volume. If I put it in a smaller container, it takes up less. But liquids and solids will not change their volume. And then that leaves us to D. D has a variable volume. Variable means to change. Gases. Which one has the most energy? Gases. Particles moving around the most. Which one has the least energy? Solid. Remember, those particles, like below it, are just vibrating in a fixed position. They're not moving around a whole lot. But they are moving. Alright, so H. Particles slide by each other but don't escape. In liquids, they're sliding by each other. When they escape, they turn into a gas. So if they've had escaped already, then we'd call them a gas. They're just zipping around, banging into each other randomly. But when they slide by each other, they're definitely a liquid. And flows, gases and liquid both flow. Both gases and liquids flow. Okay, it says, imagine a beaker containing a salt water solution. Is this a homogeneous or heterogeneous? Remember, homo means it all looks the same. You can't tell the different parts apart. And heterogeneous means you can identify the different components of the mixture. Now, it tells you it's a salt water, so you can probably picture that. You can't see the individual salt particles if it's an actual salt water solution. And on top of it, the word solution is a major clue here. Solution is a synonym for the word homogeneous mixture. So solution and homogeneous mixture are the exact same thing. Homo means same. It looks the same throughout. Now B says, draw a quick sketch of a typical distillation apparatus and explain how the distillation process can be used to separate the salt from the water. Well, I didn't draw it here, but I just copy and pasted it in a picture. But you can see the Bunsen burner down here providing heat. Here's your container of your original substance, the salt water solution. Here's a stopper, so whenever you heat this, whatever you're heating can't get out. Instead, it's going to go down this little sidearm flask, and it's going to go down, down, down this condenser tube, which is basically a tube within a tube. You can see the little tube in the inside here, and then it pours out into this other collection container. So what's going to happen is you put the saltwater solution here, and let's read the answer. The saltwater solution is placed in the flask and heated. The temperature rises until the boiling point of water is reached. The salt is not going to boil at these temperatures, so we're just going to heat the water up. The water is going to start boiling at 100 degrees. Only the water boils. The salt does not boil, so the salt is going to stay down here. The water boils, turns into gas, and it rises, 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 bangs into this stopper up here. it can't get out through the top, so instead it goes down the side arm and it goes into the condenser tube. Remember, we still have hot, happy gas molecules zipping around. So then they move down the condenser tube and they lose energy because the condenser tube has cold water running around the outside of the inner tube. So around the outside of this inner tube is cold water. We force the cold water in, force it against gravity, it goes up, and then it comes back out here when it warms up a little bit. So we're cooling off all the gas particles inside that condenser tube by giving it, or putting cold water around it, which is taking the energy away. When we take the energy away, the gas particles lose their energy and become condensed. They become liquid particles, and then you can see the liquid pouring out here into your collection flask. Now this is going to be pure water, no salt. The salt never boiled, the salt stayed up here. So we can separate the two, the salt and the water, by boiling off the water and collecting it here and leaving the salt in our container. C says, what temperature would you expect the thermometer to read when the water is boiling? 100 degrees. At standard sea level, atmospheric pressure, it's going to be 100 degrees. You can identify a substance. For instance, if it was boiling at 50 degrees, you know it's not water. If it's boiling at 108 degrees, you know it's not water. What is the primary purpose of running water through the condenser tube? We just mentioned this. The water's job, running around the condenser tube, is to remove energy from the vapors inside the condenser tube so they can condense back into the liquid form. If you don't remove the energy, if you never run water through that condenser tube, then the gas particles are going to go in here and come right back out and then escape into the air. So they'll remain a gas and escape out of the other end of the tube as a gas, and we can't collect anything, so it's useless to even run this experiment. Okay, so that's that concept. Number 16, it says all matter is made up of tiny particles called atoms. And then over here, number 17, we have to determine the number of oxygen atoms in the following samples. So we're going to take a look at how many atoms we have in each. Now this requires some distribution, just like in your math class. Okay, so this first example, we have a big 2 out front. That's telling us we have 2 molecules of this stuff. Now the one molecule contains 6 oxygens. So we're going to go 2 times 6. 2 times 6. Let me pick a different color here. So 2 times 6 is going to be 12 oxygens. You could just think of it as one of these guys and another one of those. 6 and 6 is 12. Over here we have 3 sets of sulfate. So technically we have SO4, SO4, and SO4. And then that's 4, 4, and 4. That's 12 oxygens. The other way you can get that is say, well, there's 4 oxygens in the sulfate, and we have 3 sulfates, so 3 times 4 is 12. You can distribute. If you have problems with that, you're not sure exactly what you do, just think about it logically. This tells us we have 3 sulfates, each of them has 4. 4 times 3 is 12. And over here, you distribute the big coefficient again. 3 times 3 is 9.